December 1944, Typhoon Cobra. 140-mile-per-hour winds tear across the Philippines. Wooden buildings explode into splinters. Concrete structures collapse. But 39 curved steel tunnels remain standing, their occupants alive inside while everything around them disintegrates. March 1942. A warehouse in Rhode Island. 30 engineers. 60 days to design a building that doesn't exist yet. A structure that must be lighter than a Jeep, assemble in 8 hours, cost less than $1,000, and survive conditions that destroy permanent construction. The deadline is impossible. The requirements are contradictory, and 2 million American servicemen are about to depend on them getting it right. August 1942. Guadalcanal. Marine engineers bolt together steel panels under artillery fire, building shelter while Japanese bombers make their daily runs. 12 hours later, Henderson Field has structures that will house the men keeping America's battered fighters in the air. 3 days after that, a 500-pound bomb detonates 40 yards away. The blast flattens palm trees. The men inside the curved steel shelter walk away without a scratch. February 1945. Iwo Jima. Black volcanic sand. No topsoil. Constant artillery from Mount Suribachi. Construction crews arrive on D-Day +2 and start assembling buildings, while mortar rounds impact 200 yards away. When the Pacific typhoon hits in March with 110-mile-per-hour winds, these improvised structures hold while everything else vanishes. This is the story of the Quonset hut. The curved steel structure that housed millions during World War II survived the worst that nature and enemy action could deliver, cost 1/10 what conventional buildings did, and accidentally revolutionized architecture in ways its designers never imagined. You're about to discover how American engineers solved an impossible equation in 60 days flat. How corrugated steel geometry borrowed from farm buildings became the backbone of Pacific logistics. How a design meant to be temporary kept working for 80 years. And why, when NASA plans Mars habitats, when the UN houses refugees, when disaster zones need immediate shelter, they keep rediscovering the same principles that emerged from that Rhode Island warehouse in the spring of 1942. The secret wasn't just good engineering. It was engineering under pressure so extreme it forced innovation that conventional thinking would never produce. This is how you design a building that can be assembled by exhausted Marines who've never held a wrench, survive Category 5 typhoons, ship 10,000 miles through submarine-infested waters, and still be standing when your great-grandchildren visit it as a historical landmark. Let's begin where it all began, with a crisis. Act 1. The Impossible Equation, December 7, 1941. Pearl Harbor burns. Within 72 hours, the United States military faces a logistics nightmare that has absolutely nothing to do with destroyed battleships or damaged aircraft. Across the Pacific theater, from the Philippines to Wake Island, American forces are sleeping in canvas tents that disintegrate under tropical downpours within 3 weeks. Field reports arrive at the War Department's morning briefings describing entire supply depots flooded, ammunition ruined, and soldiers hospitalized with pneumonia because their shelter literally fell apart during monsoon season. The numbers are grim. Traditional wooden barracks require skilled carpenters, weeks of construction time, and most critically, lumber that simply doesn't exist on remote coral atolls. The Navy calculates it would take 18 months to build conventional housing for the forces they need to deploy immediately. 18 months! The war might be over by then, won or lost, based on whether America can project force across the Pacific faster than Japan can consolidate its captured territories. In Washington, Brigadier General Eugene Raybould stands before a crisis table covered in weather maps and construction timelines that all tell the same story. His engineers present the impossible equation with the bluntness of men who've run the numbers a dozen times, hoping for different results, They need structures that can be manufactured in Pennsylvania steel country, shipped 10,000 miles through waters patrolled by German U-boats and Japanese submarines, assembled by exhausted Marines who might have never held a wrench before basic training, and survive everything the Pacific can possibly throw at them. 130-degree heat that turns metal into a cooking surface. Category 5 typhoons with winds exceeding 150 miles per hour. Monsoons that dump 15 inches of rain in 6 hours. Jungle humidity that grows fungus on anything organic within days. And the very real possibility of Japanese bombing runs turning any concentration of American structures into priority targets. The standard Army tent costs $12 but lasts exactly 1 month in jungle. Conditions before the canvas rots through. A wooden barracks building costs $8,000 and requires a skilled construction crew for 6 weeks, assuming you can find the lumber, which you can't, and assuming the construction site isn't within artillery range, which it often is. Neither option works when you're island hopping across the Pacific and need shelter for 50,000 men yesterday. The British have been fighting this war longer, and their experience offers a clue. Since 1916, they've used Nissen huts in their military operations. These semicircular steel shelters were invented by a Canadian engineer named Peter Nissen during World War I, and they've proven themselves across multiple theaters. Corrugated iron half-cylinders that house 30 soldiers require no skilled labor to erect, and laugh at sandstorms that would shred canvas tents. British Nissen huts have seen service in Mesopotamia, France, North Africa, and now Libya, where General Montgomery's desert forces use them extensively. The design has genuine merit. The arch shape naturally sheds wind and rain. The corrugated steel is durable. The modular construction means you can add units together to create larger facilities. But the Nissen design has critical flaws for Pacific deployment, and these flaws are serious enough to make the British design unsuitable without fundamental redesign. The British version uses heavy steel panels that need specialized lifting equipment to move and position. Each panel weighs over 100 pounds, which means assembly requires either mechanical hoists or large crews of men. In the Pacific, where you might be building on a beach under fire, neither option is practical. The ventilation system was designed for the Libyan desert, where the problem is heat but relatively low humidity. In the Philippine jungle, where humidity regularly exceeds 90% and temperatures hover around 95 degrees, the Nissen hut's ventilation turns the interior into what soldiers accurately describe as a steel sauna. Men sleeping in poorly ventilated Nissen huts in tropical conditions wake up drenched in sweat, and the moisture condenses on the interior steel surfaces, literally raining back down on them. Most damaging to rapid deployment plans. Each British Nissen hut requires custom foundation work. You need to pour concrete pads or build wooden platforms to create a level surface and provide anchor points for the structure. This foundation work brings you right back to the carpenter problem, the time problem, and the skilled labor problem. Raybold's team calculates they need shelter for 2 million personnel across hundreds of islands and forward bases. The math is brutal and unforgiving. At conventional construction rates, even with a massive mobilization of construction resources, the war would be over before half the troops had permanent roofs over their heads. The letters from the Pacific make the abstract numbers painfully concrete. Soldiers write home describing how they wake up with their boots full of rainwater, how fungus grows on their uniforms overnight, turning fabric green and weakening seams until sleeves tear off, how temporary tents collapse during storms, sending men scrambling in the mud at 3 in the morning to rescue their gear before it washes away, how you learn to sleep sitting up with your rifle and pack elevated off the ground because the floor of your tent becomes a river when it rains. The Medical Corps reports numbers that alarm senior command. In some sectors, respiratory infections from inadequate shelter are hospitalizing more men than enemy action. Pneumonia, bronchitis, and persistent fungal infections are degrading combat effectiveness before units ever see battle. This isn't about comfort or morale, though those matter. This is about maintaining a fighting force that doesn't literally rot away before engaging the enemy. The call goes out in January 1942 to American engineering firms, university research departments, and the Navy's own construction battalions. The specification document reads like science fiction, or perhaps like a wish list written by someone who doesn't understand the fundamental constraints of construction. Design a building that weighs less than a jeep, but houses 36 men. Make it fit on a single rail car for shipping. Require no foundation work whatsoever. Assemble in one day with basic hand tools. Cost less than $1,000 in materials. Survive conditions that routinely destroy permanent buildings. Oh, and have 10,000 units ready to ship within 6 months. Most firms look at these requirements and politely decline. The weight requirement alone seems impossible. A Jeep weighs about 2,200 pounds. A building that houses 36 people and survives typhoons should weigh several tons at minimum, not less than a small vehicle. The no foundation requirement contradicts basic engineering principles. Buildings stay standing because they're anchored to something solid. How do you anchor a structure to loose sand or coral rubble without foundation work? The one-day assembly timeline with unskilled labor sounds like wishful thinking from people who've never actually built anything. But it's February 1942. The Philippines are falling. Singapore will surrender in days. The Japanese advance seems unstoppable, and the only thing that might slow them down is America's ability to build, supply, and sustain forward bases faster than Japan can capture territory. In Rhode Island, at the newly commissioned Quonset Point Naval Air Station, a team of engineers is about to turn this impossible specification into reality, not through inspiration or genius, but through pressure so intense it forces innovation that decades of peacetime thinking never produced. A-Seat 2. Borrowed Genius. 3D Nissen Hut blueprint arrives at the Navy's Bureau of Yards and Docks in March 1942 as part of a peculiar twist of wartime cooperation. British engineers, grateful for American supply. Shipments keeping their war effort afloat. Share detailed technical drawings of their World War I shelter design. Commander John Philip. Drosfeld spreads the specifications across his desk and studies them with the eye of a man who's spent 20 years in naval construction. He sees immediately both the genius and the fatal problems. The genius is elegant and rooted in fundamental physics. The semicircular arch shape naturally deflects wind and sheds water without requiring complex engineering. When wind hits a curved surface, it flows around rather than pushing directly against it. When rain falls on an arch, gravity pulls it down and off without creating pressure points where leaks develop. The curve is self-supporting in ways that flat or angled surfaces simply aren't. But the problems fill a page of notes in Drosfeld's meticulous handwriting. The British huts weigh 3 tons when disassembled. That's 6,000 pounds of steel and fittings. Shipping that weight across the Pacific means dedicating cargo space that could carry ammunition, food, or medicine. The economics don't work when you need tens of thousands of units. The structure requires foundation bolts drilled into concrete. This means each installation site needs either existing concrete slabs or fresh concrete work, which requires cement, water, skilled labor, and most importantly, time. Time to cure. Time that American forces advancing across the Pacific don't have. The internal wooden frame that provides structural support in the British design is a feast for termites in tropical climates. Drosfeld has seen reports from British operations in Burma where wooden structural members were reduced to hollow shells within a single season. The insects don't just weaken the wood. They can make it structurally unsound so quickly that buildings collapse without warning. Drosfeld circles the ventilation specifications in red ink. 2 small windows designed for Scottish weather conditions. would turn these structures into ovens at Guadalcanal's 98-degree average temperature with 90% humidity. But there's another voice in this conversation, and it comes from an unexpected corner of architectural thinking. Buckminster Fuller has been preaching the gospel of prefabricated housing since the 1920s, though most architects dismiss him as a crank with impractical ideas. His Damaxian house concept reads like science fiction: factory-built housing units, lightweight materials assembled on site, mass production methods borrowed from automotive manufacturing, structures designed for rapid deployment anywhere. In peacetime, when conventional construction works fine and experimental architecture is risky, Fuller's ideas sound like expensive novelty. But in 1942, when conventional construction can't possibly meet the demand and speed matters more than precedent, Fuller's core insights suddenly sound prophetic. Treat buildings like manufactured products, not construction projects. Design for rapid assembly by unskilled workers. Use industrial materials instead of traditional lumber. Optimize for shipping efficiency. The military hasn't directly consulted Fuller, but his published papers circulate through engineering departments, and his philosophy influences the thinking of engineers trying to solve this impossible problem. The Navy consolidates this design work at their facility at Quonset Point, Rhode Island. The location isn't random or convenient. Rhode Island has deep manufacturing expertise in sheet metal work, from its jewelry and silverware industries. The state sits close to steel mills in Pennsylvania and shipyards that understand marine-grade corrosion resistance. And perhaps most importantly, it's far from any combat zone, meaning designers can work without worrying about air raids disrupting their prototype work. In March 1942, the Navy assembles what one participant later calls the most unlikely team ever formed to design anything. Structural engineers from the Strand Steel Corporation, who've spent their careers building prefabricated farm buildings. Architects from George A. Fuller Construction Company, who specialize in rapid assembly methods. Navy officers who've actually served in the Pacific and know the difference between what typhoon-proof means on paper versus what it means when you're experiencing a real typhoon with 150-mile-per-hour winds trying to peel your shelter like a sardine can. The team lead is Otto Brandenberger, and his background turns out to be exactly right for this seemingly impossible challenge. He's spent years designing strand steel agricultural buildings, the big arch-roofed barns you see on Midwestern farms. These buildings use self-supporting curved metal panels with no internal wooden framing, which means there's no skeleton for termites to eat and no complex joinery to fail during storms. Brandenberger makes a proposal so radical that conventional architects in 1942 consider it almost reckless. Eliminate the Nissen hut's wooden skeleton entirely. Make the corrugated steel skin carry all the structural loads itself. This violates conventional architectural wisdom where steel is for bridges and skyscrapers, not for creating self-supporting building shells. But Brandenberger knows from farm building experience that his arch-roofed barns have survived Midwest tornadoes without any internal framing. He's willing to bet the same principle scales up to military housing. The British contribute something equally valuable through their painful operational experience. Their Nissen huts in Burma, Singapore, and North Africa have taught them exactly how tropical environments destroy buildings, and their detailed reports read like horror stories with useful data. Fungus isn't just cosmetic discoloration. It literally eats through wood preservatives and paint within months, getting into the grain and destroying structural integrity from the inside out. Humidity doesn't just make things damp and uncomfortable. It corrodes metal fasteners until roofs collapse. The salt air in coastal areas accelerates this corrosion by orders of magnitude. Insects aren't merely annoying. Carpenter ants and termites can reduce wooden support beams to hollow shells in one season, leaving buildings standing only because no one has stressed the compromised structure yet. These British reports provide the Quonset team with a checklist of everything that must be engineered out of the design from day one. Every weakness that tropical service will exploit. Every failure mode that seems minor in Rhode Island but becomes catastrophic in Guadalcanal. No wood in contact with ground. All steel must be hot-dip galvanized, not just painted. Ventilation must be aggressive enough to prevent condensation. Every fastener must be accessible for replacement without disassembling the entire structure. By April 1942, the hybrid vision crystallizes in a series of design meetings where theoretical engineers clash with practical field experience. And the result is something neither group would have developed independently. Take the Nissen hut's brilliant arch geometry that's been proven in combat. Strip out everything that makes it heavy, slow to assemble, or vulnerable to environmental degradation. Add Fuller's mass production philosophy and American steel manufacturing capability. Then engineer every single detail specifically for the particular hell of Pacific Island warfare. The result on paper looks promising. Whether it will actually work under real conditions is another question entirely. And they have 60 days to find out. HT3. 60 days to miracle, April 15th, 1942. Otto Brandenburger walks into a warehouse at Quonset Point with 30 engineers. A stack of blueprints that are more concept sketches than finished designs. And a deadline that would be laughable if the war situation weren't so desperate. 10 days, 2 months, 8 weeks to design, prototype, test, and approve a completely new building system that doesn't yet exist in any functional form. The team works in shifts around the clock. Engineers sleep on cots pushed against the warehouse walls. They subsist on Navy mess hall coffee, cigarettes, and the kind of pressure that either produces brilliance or complete nervous collapse. Brandenburger divides his crew into specialist teams because tackling all the problems simultaneously is the only way to meet the deadline. One group handles aerodynamics and structural loading calculations. Another figures out how to nest components efficiently for shipping. A third works exclusively on the joint and fastener problem that plagued the British design. The first radical decision happens on day 3, and it violates every established procedure for how buildings get designed. Traditional architectural practice in 1942 requires complete drawings before cutting a single piece of material. Architects spend weeks or months producing detailed specifications. Only after every dimension is documented and approved does fabrication begin. This deliberate process prevents expensive mistakes, but it takes time that the Quonset team absolutely doesn't have. Instead, they build in real time using what would later be called rapid prototyping. Sketch a detail in the morning. Have the metalworking shop fabricate it by afternoon. Test it overnight. Revise by dawn based on how it failed. This iterative approach is standard practice in 2025, but it's revolutionary in 1942 when buildings are designed entirely on paper before physical construction begins. The warehouse floor becomes a laboratory scattered with failed joint experiments, bent test panels, and increasingly refined versions of each component. The engineers borrow a technique from aircraft manufacturing, giving every part a number and documenting every revision so that improvements don't get lost and mistakes don't get repeated. The dimensions emerge from brutal practicality rather than aesthetic choice or traditional architectural proportions. 10 feet wide. This is the maximum width that fits on a standard rail car without requiring special permits or route planning. Make it narrower and you're wasting shipping capacity. Make it wider, and suddenly you're dealing with oversized load regulations that slow everything down. Feet long per section. Short enough that 4 men can lift and position a panel without mechanical assistance. Long enough to create usable interior space. The math of human lifting capacity dictates this dimension as clearly as any engineering calculation. To feet total length when fully assembled. This provides housing capacity for 36 men with bunks, or converts to office space, medical stations, or supply storage. The number isn't arbitrary. It's based on military planning standards for squad and platoon organization. The Quonset team discovers these dimensions hit a sweet spot in structural engineering where multiple constraints align. Make it smaller, and you waste shipping capacity and provide inadequate interior space. Make it larger, and the panels become too heavy for field assembly. Or the arch structure starts requiring internal supports that reintroduce all the complexity they're trying to eliminate. The arch radius calculation consumes 2 full weeks of the 60-day deadline. And this is time well spent, because getting this wrong means catastrophic failure. Too flat an arch and wind forces can peel the structure apart like opening a sardine can. Too steep, and you waste precious interior headroom while creating difficult end wall geometry that complicates manufacturing. Brandenburger's team settles on an 8-foot radius, creating a perfect semicircle. This provides 7 feet of headroom at the sides where men will be walking and working. More importantly, it creates what structural engineers call a self-bracing arch. The corrugated steel naturally wants to hold this curve. The material's own stiffness provides structural resistance. This means the panels can be thinner and lighter than flat sheets would require for the same load-bearing strength. Weight savings compound throughout the design. Lighter panels mean easier shipping, faster assembly, and lower material costs. They run preliminary load calculations showing this design should theoretically handle snow loads up to 40 pounds per square foot and wind speeds exceeding 100 miles per hour. These are impressive numbers on paper, but theoretical calculations and real Pacific typhoons are very different animals. By day 40 of the 60-day sprint, they have something that looks like it might actually work. A prototype assembled from riveted panels, experimental joints, and borrowed hardware stands in the warehouse looking like a gigantic steel tunnel half buried in the ground. The first complete prototype goes up on May 25, 1942, assembled by 6 sailors who've been given 4 hours of instruction and issued basic hand tools. The team times the assembly carefully because meeting the 1-day requirement is crucial to the entire concept. Assembly time, 14 hours. This is encouraging, but not good enough. The Navy specification calls for single-day construction capability because marine landing schedules don't allow for multi-day building projects. When you're establishing a beachhead, you need shelter operational before nightfall, not tomorrow evening. The team identifies the bottleneck immediately. It's the floor system. They've been trying to include a finished wooden floor as part of the basic package, but floor installation is the slowest part of assembly and creates a different problem. That wood is the first thing to rot in tropical conditions anyway. The solution is elegant in its radical simplicity. Eliminate the floor entirely from the basic design. The Quonset hut sits directly on whatever surface exists: coral gravel, sand, dirt, or if you're lucky, existing hardstand. For applications requiring finished floors, those can be added later as a separate construction project using local labor and materials. But the basic shelter achieves weather protection without flooring. This single decision cuts assembly time to 8 hours and reduces shipping weight by 1/200 pounds per unit. 8 hours fits within a single workday. The weight reduction means each ship can carry more units. On June 10, 1942, the final prototype stands complete in the Quonset Point warehouse. 96 corrugated steel panels, each weighing less than 50 pounds, bolt together to create 720 square feet of enclosed space. Total materials cost $1,394, just under the $1,400 target. Total weight, 9,000 pounds. Well under the lighter than you'd expect threshold, though heavier than a Jeep. But now comes the real test. The engineering equivalent of an interrogation designed to find every possible failure point before American lives depend on this design working under combat conditions. A-Seat 4. Trial by numbers, Navy structural engineers arrive at Quonset. Point in June 1942 with wind load tables, typhoon data from meteorological stations across the Pacific, and healthy skepticism that this corrugated tunnel can survive what nature throws at tropical islands. The numbers they're working with aren't theoretical projections or safety factor estimates. They're pulled from actual weather events that destroyed conventional structures. Typhoon Gloria hit Guam in November 1940 with sustained winds of 100 40s miles per hour and gusts reaching 180. The 1935 Labor Day hurricane that killed 400 people in the Florida Keys produced winds so powerful they sandblasted paint off buildings and drove wooden planks through palm trees like spears. If Quonset huts fail in storms like these, the result isn't just property damage and insurance claims. It's dead American servicemen and destroyed military equipment. Brandenburger's team starts their defense with the fundamental physics of why arch shapes work. And this requires explaining pressure coefficients and wind dynamics in ways that non-engineers can understand. When wind hits a flat wall, it creates maximum pressure. The wind pushes directly against the surface with its full force. Engineers measure this with something called a pressure coefficient, essentially a number representing how much force the wind exerts per square foot of surface. But a curved surface changes everything. Wind hitting a semicircular arch doesn't push directly against it. The curve deflects the wind upward and around, reducing that pressure dramatically. Think of how water flows around a smooth river stone versus slamming into a dam wall. The stone experiences less force because the water flows around it rather than stopping dead. The Quonset profile means hurricane-force winds slide over the structure rather than trying to punch through it. This isn't just theory. It's the same principle that keeps airplane wings from being ripped off in turbulence. The corrugations add a second layer of structural brilliance that the Navy engineers immediately recognize. Those ridges running lengthwise create rigidity, the way folding a piece of paper makes it stronger than leaving it flat. Each corrugation acts like a miniature I-beam, resisting bending forces that would crumple smooth sheet metal. The structural analysis gets fascinating when you examine how loads distribute through the arch. In a conventional rectangular building, the roof pushes down on walls, the walls push down on foundations, and everything depends on those vertical load paths staying intact. Storm winds can literally lift roofs off because they're separate elements just sitting on top of walls, held down by gravity and fasteners. The Quonset arch changes this fundamental relationship. It's a single continuous curve where every panel shares loads with its neighbors. Engineers call this a compression ring, and it operates on the same principle that keeps stone bridges standing for centuries without mortar. The arch wants to spread apart at its base, creating what engineers call hoop stress or ring tension. But when you bolt the base to the ground, that outward force gets resolved into the earth itself. Meanwhile, the arch geometry converts vertical loads from snow or wind into compression forces that the curved shape is perfectly designed to handle. Each Quonset panel bolts to adjacent panels with 3 to 4 inch steel bolts spaced every 6 inches. This creates what's essentially a 48-foot-long steel cable wrapped in an arch shape. The overlapping panels share stress. If one section weakens, neighboring sections help carry the load. But theoretical strength means nothing without empirical testing. So the Navy sets up validation experiments that border on structural sadism. They build a full-scale Quonset hut at Davisville, Rhode Island, and instrument it with strain gauges to measure how much the steel flexes under load, pressure sensors to track wind forces, and deflection meters to record any movement in the structure. Then they wait for the first major nor'easter. How engineers designed Quonset huts to survive storms, bombs, and jungle heat part 2 of 2. YouTube script, final 5,000 words. Act 4, continued, Nature's Stress Testin'. March 3, 1943. A massive nor'easter slams into the Rhode Island coast with 75-mile-per-hour winds and heavy snow loading. Perfect test conditions, though the timing is accidental. The Navy engineers monitoring the instrumented Quonset hut at Davisville watch their gauges intently as the storm builds in intensity. The strain gauges record the structure flexing at the crown, the highest point of the arch, by less than 2 inches. Then, as the wind subsides, the steel springs back to its original shape. The panel joints hold, nothing leaks. The bolted connections show no signs of loosening or fatigue. The structure behaves exactly as the calculations predicted, which is simultaneously thrilling and slightly terrifying because it means they're about to bet thousands of American lives on this design working correctly under far worse conditions than a New England winter storm. The tropical environment testing proves more challenging than wind loads because you cannot simulate years of jungle conditions in a Rhode Island warehouse. Chemistry and biology don't speed up just because you're in a hurry. The Navy ships a test unit to the Panama Canal zone where humidity averages 85% year-round and temperatures stay above 80 degrees. This is as close as you can get to Pacific conditions without actually deploying to a combat zone. 6 months later, the detailed report arrives back at Quonset Point. Minimal corrosion on the galvanized panels. The zinc coating is doing its job, sacrificing itself to oxidation, so the underlying steel remains protected. No structural degradation from the heat or humidity. The arch shape maintains its integrity, but there are serious problems with interior condensation that need immediate solving. When hot, humid air hits the relatively cooler steel surfaces at night, water vapor condenses and literally rains from the ceiling inside the hut. Men sleeping inside wake up soaked. Not from leaking, but from moisture condensing on the interior steel and dripping down. This isn't just uncomfortable. In tropical conditions, this constant moisture creates breeding grounds for mold and bacteria. The solution requires adding ventilation louvers at both ends of the structure and along the ridgeline. These are openings that let hot air escape and create continuous airflow through the building without compromising structural strength or weather protection during storms. The vents add $47 to the unit cost, but they transform the Quonset hut from a steel sauna into something humans can actually occupy in tropical heat. The temperature inside drops by 15 to 20 degrees when air can circulate. Just as importantly, the moving air prevents condensation from forming in the first place. The final engineering challenge is the foundation question, and it's the problem that plagued the British Nyssen huts. How do you anchor a 9,000-pound building to loose sand or coral without pouring concrete foundations? The answer comes from tent technology scaled up to industrial strength. Steel stakes, essentially giant versions of tent stakes but made from half-inch steel rod, get driven into the ground at angles. Adjustable tension cables connect these stakes to the hut's base panels. The cables can be tightened or loosened to level the structure on uneven ground. For harder surfaces like coral or existing concrete, the team designs a bolt pattern that lets the hut mount directly to wooden sleepers or pierced steel planking. The beauty of this system is its flexibility. The structure can shift slightly with ground movement without tearing itself apart. This matters enormously in combat zones where nearby explosions can shift soil and where you might be building on ground that's not fully stable. ECT-5. Industrial Mobilization June 1942. The War Production Board approves Quonset hut manufacturing, and what happens next demonstrates American industrial capacity operating at its absolute peak. The Navy contracts with 10 major steel fabricators across the Midwest and Northeast. These are companies that 6 months ago were making grain silos, water tanks, and agricultural buildings. Now they're retooling their entire operations for military shelter production. The Strand Steel Corporation converts its Penrose facility outside Philadelphia to exclusive Quonset production. George A. Fuller Construction takes over a former automobile parts plant in Chicago. Great Lakes Steel dedicates 2 complete rolling mills to nothing but corrugated panel production. By August 1942, these factories are collectively producing 1,500 complete huts per week. The number keeps climbing as production lines optimize their processes and suppliers deliver materials in greater quantities. The manufacturing process borrows heavily from automotive assembly line logic, turning building construction into mass production. Massive steel coils arrive by rail from mills in Pennsylvania and Ohio. Each coil is 4 feet wide and contains enough raw material for 30 panels. Rolling machines take this flat steel and run it through corrugating dies, creating those structural ridges at precisely 2.67 inches on center. The corrugating process actually work hardens the steel, making it stronger than the flat sheet that went in. Next, the corrugated panels go through galvanizing tanks where they're dipped in molten zinc heated to 850 degrees Fahrenheit. This isn't paint that sits on the surface. It's a metallurgical bond where zinc atoms fuse with the steel surface. The zinc coating sacrifices itself to corrosion before the underlying steel can rust. In Pacific saltwater air, this galvanizing means the difference between a 5-year lifespan and a 50-year lifespan. The process costs an extra $112 per hut, but field reports from early deployments show that ungalvanized test units corrode through in just 8 months. The extra cost is non-negotiable. Each complete hut kit gets packaged with obsessive attention to shipping logistics because cargo space on ships heading to the Pacific is precious. The 96 corrugated panels nest inside each other like stacked bowls, reducing the package height from 8 feet to just 14 inches. This nesting efficiency is crucial. The end walls, made from plywood sheets with pre-cut door and window openings, pack flat between the steel panels. All fasteners, bolts, washers, and hardware get boxed in a single wooden crate that includes illustrated assembly instructions designed for men who might not read English fluently. The instructions use pictures and diagrams with minimal text, borrowing techniques from IKEA furniture manuals that won't be invented for another 40 years. The entire kit loads onto one standard flatbed railcar measuring 40 feet long. This packaging density matters enormously because every train heading to West Coast ports carries either Quonset huts, ammunition, food, medical supplies, or vehicles. There is zero room for inefficient cargo. Everything must pack as tightly as physics allows. The shipping choreography gets impressively complex. Trains leave Philadelphia and Chicago daily, arriving at San Francisco, San Diego, and Seattle, where Liberty ships and specialized cargo vessels wait at the docks. Longshoremen load complete huts into ship holds, using the same crane systems designed for tanks and artillery pieces. A single Liberty ship can carry 200 Quonset huts, plus their assembly hardware. That represents shelter for 7,200 men. The War Shipping Administration tracks every cargo manifest with the precision of accountants because these aren't just buildings. They're strategic assets that directly enable forward operations. A Quonset hut that ships from Philadelphia in September might house a bomber crew at Guadalcanal by October, making the difference between operational aircraft and pilots sleeping in mud, unable to fly their missions. The assembly process on the receiving end is where the Quonset design genius really proves itself. The Navy's construction battalions, the famous Seabees, develop standardized procedures that turn shelter erection into a choreographed operation anyone can learn. 6-man crew. 8 hours. 1 complete hut ready for occupation. The process starts with site preparation that takes maybe an hour if the ground is cooperative. Level the surface as much as possible. Remove vegetation that might hold moisture against the steel. Lay down a gravel base if materials are available, though this is optional rather than required. 2 men handle the end walls while 4 wrestle the steel panels into position. The panels overlap by 6 inches and bolt together with those 3/4-inch fasteners. No welding required, no concrete needed, no skilled trades necessary. Just wrenches, a level, and men who follow the illustrated instructions. The WWII speed record gets set on Espiritu Santo in January 1943, when a specially trained CB crew erects a complete hut in 4 hours and 17 minutes. But that's showboating for a visiting admiral. The real achievement is sustained production across hundreds of islands, where crews throw up 5 or 6 huts per day. Day after day, building entire military bases faster than the Japanese can bomb them back into rubble. By December 1943, monthly production hits 8,000 units. The logistics network moves so efficiently that huts ordered in Pennsylvania reach New Guinea within 40 days, including ocean crossing and trans-Pacific transport through submarine-patrolled waters. The cost accounting tells a compelling story of industrial efficiency. Each Quonset hut provides 36 men with weatherproof shelter for 1,394 in materials and approximately 60 man-hours of assembly labor. Compare this to conventional wooden barracks that cost $12,000 in materials, require 400 man-hours of skilled carpentry, and take 6 weeks to construct. The Quonset delivers shelter at 1/10 the cost in 1/20 the time. These aren't trivial improvements. They're the difference between adequate shelter and chronic homelessness for American forces island hopping across the Pacific. By mid-1944, the U.S. military has deployed over 160,000 units to every combat theater. That's housing capacity for nearly 6 million personnel, built in less than 2 years. No conventional construction program could have achieved this scale and speed. ACTV C. Eric's Combat Validation Guadalcanal, August 1942. The first combat-deployed Quonset huts arrive on a beach where the temperature hovers at 95 degrees with 90% humidity, and Japanese bombers make daily visits to crater anything that looks like American infrastructure. Marine engineers unload the flat-packed steel panels under sporadic artillery, fire and start bolting them together in a coconut grove still showing scorch marks from the previous week's shelling. The air smells like burning vegetation and cordite. Men work in steel helmets because sniper fire from the jungle remains a constant threat. Within 12 hours, Henderson Field has 10 new structures housing maintenance crews for the battered F-4F Wildcats operating from the airstrip. These aren't rear echelon facilities built in safety. These are frontline shelters assembled under combat conditions. The real test comes 3 days later when a Japanese bombing run scores a near miss. A 500-pound bomb detonates 40 yards from a Quonset hut full of aviation mechanics working on engine repairs. The blast wave flattens surrounding palm trees and shreds canvas tents like tissue paper. The shock wave is powerful enough to knock men off their feet inside the hut. But the Quonset flexes. The arch shape deflects the blast pressure upward and around. Dirt and shrapnel rattle off the corrugated steel like hail on a tin roof. When the smoke clears and ears stop ringing, the structure stands intact with every man inside shaken but alive and uninjured. This survival isn't luck. It's geometry and physics working exactly as designed. The blast wave hits a curved surface that deflects force rather than absorbing it directly. The overlapping panel construction means even if shrapnel penetrates one panel, the damage stays localized rather than triggering catastrophic structural failure. The jungle environment proves as hostile as enemy action. Within 2 weeks, red rust streaks appear on any fasteners that weren't properly galvanized. The salt air eats through standard hardware like acid. Fungus grows on everything that holds moisture, turning inside surfaces into abstract art exhibits of black and green mold. The ventilation louvers that seemed adequate during Rhode Island testing barely move the suffocating tropical air. Marines start propping doors open 24 hours a day and cutting additional vent holes with tin snips. These field modifications technically violate structural specifications, but they make the huts livable in conditions that would be intolerable otherwise. These improvised solutions get documented in after-action reports and sent back to Quonset Point, where engineers incorporate them into later production runs. More ventilation, larger louvers, every single fastener galvanized regardless of its location or supposed protection from weather. This feedback loop between combat experience and factory production demonstrates adaptive engineering at its best. The design evolves based on real-world performance rather than theoretical assumptions. Iwo Jima, February 1945. The volcanic island offers a different kind of hell for construction. Black sand blows into every crevice. There's no topsoil for driving ground stakes. Japanese artillery from Mount Suribachi maintains constant harassing fire on the beach. Seabees arrive on D-Day +2 and start assembling Quonset huts under fire, literally bolting panels together while mortar rounds impact 200 yards away. The volcanic sand proves impossible for traditional stake anchoring. Driving stakes into loose sand is like trying to anchor a tent in a sandbox. The stakes pull out under any lateral force. Crews improvise by filling empty 55-gallon oil drums with sand and connecting them to the hut bases with cables. These improvised anchors weigh 400 pounds each when filled. 8 drums per hut provide sufficient holding force even in the loose volcanic soil. When a Pacific typhoon hits in March with 110-mile-per-hour winds, those improvised anchors hold while wooden structures across the island disintegrate. The base commander's report back to Pearl Harbor is succinct and impressive. Quonset huts survived. Everything else gone. The Arctic environment tests the design from the opposite extreme. Alaska's Aleutian Islands campaign sees Quonset huts deployed at Dutch Harbor and Adak, where temperatures plunge to -40 degrees and winds regularly exceed 100 miles per hour. The cold makes the steel brittle, and early units suffer from panels cracking at the bolt holes where stress concentrates. Engineers respond by specifying cold-rolled steel with different metallurgy for Arctic deployments. The new steel formulation maintains flexibility at extreme low temperatures. Heating the huts creates its own set of problems. Warm air meeting frozen steel produces condensation that literally rains inside until crews learn to install insulation blankets and run ventilation even in sub-zero weather, which seems counterintuitive but proves necessary. By winter 1943, winterized Quonset models include internal insulation batting, double-wall construction for extreme cold zones, and modified ventilation systems that prevent heat loss while still managing moisture. North Africa and Italy bring different challenges. At Palermo, Sicily, a Quonset hut pressed into service as an ammunition depot takes a direct hit from a German 88mm artillery shell. The shell penetrates the steel skin, detonates inside among crates of small arms ammunition, and the resulting explosion should theoretically vaporize the structure. Instead, the arched-shaped channels blast force outward through the walls and roof in a pattern that leaves the structural frame twisted but still standing. Explosive ordnance disposal crews examining the wreckage note that a rectangular building would have collapsed completely, potentially trapping anyone nearby under tons of rubble. The arch's inherent strength, that compression ring effect, means even catastrophic damage doesn't trigger total structural failure. The building might be destroyed for practical purposes, but it doesn't collapse into a rubble pile. ACT-87, Typhoon Cobra. The Pacific typhoon season of 1944 delivers the ultimate stress test that validates every design. Decision made in that Rhode Island warehouse. Super Typhoon Cobra hits the Philippines in December with winds measured at 140 miles per hour and a 20-foot storm surge. At Tacloban, the storm destroys 80% of all structures on the base. Wooden buildings explode into splinters, as wind gets underneath roofs and lifts them like airplane wings. Concrete block structures collapse when storm surge undermines their foundations. But of 43 Quonset huts on the base, 39 survive intact. 4 suffer repairable damage consisting of bent panels and torn seams, but no total failures. No deaths in the Quonset huts despite winds that killed hundreds of people across the Philippines. Engineers, analyzing the survivors after the storm, find that proper anchoring matters more than any other single factor. Quonset huts with adequate ground attachment ride out the typhoon without major damage. Those with improvised or insufficient anchoring roll like tumbleweeds across the landscape. This empirical evidence leads to revised field procedures emphasizing anchor installation. Future deployment manuals specify anchor patterns and tension requirements with the precision of aircraft maintenance procedures. This isn't optional. It's mandatory for survival. By war's end in 1945, field performance data from over 50 combat zones feeds back into continuous design improvement. The production models rolling off assembly lines in 1945 bear little resemblance to the 1942 prototypes, though the basic geometry remains unchanged. Better ventilation systems with larger louvers and more airflow, stronger fasteners that resist corrosion longer, improved insulation options for different climates, field-tested modifications that turned a good design into an exceptional one. WWII. Peace Dividend. May 8, 1945, victory in Europe. August 15, 1945, victory over Japan. Suddenly, the United States military owns approximately 170,000 Quonset huts scattered across 6 continents and has absolutely no idea what to do with them. The original plan assumed these were temporary wartime expedients that would be scrapped or abandoned once permanent facilities could be built. Conventional thinking suggested soldiers would want real buildings after years of living in what amounted to glorified tin sheds. But something unexpected happens. Nobody wants to get rid of them. At hundreds of military bases slated for closure or downsizing, commanders look at their Quonset huts and see not obsolete wartime relics, but perfectly functional buildings that cost nothing to maintain, that have proven themselves under the worst conditions imaginable, and that can be repurposed for virtually anything. The War Assets Administration, tasked with liquidating surplus military property, finds itself facing an unusual problem. There's more demand for used Quonset huts than available inventory to sell. Veterans returning home discover a housing shortage so severe that families live in converted chicken coops, garages, and share apartments with 3 other families. The construction industry, starved of materials and labor during 4 years of war, cannot build fast enough to meet demand. Millions of servicemen are getting married, starting families, and needing housing immediately, not in 2 years when conventional construction might catch up. Into this crisis steps the Quonset hut, now available for civilian purchase at liquidation prices ranging from $1,000 to $2,500 for a complete structure that would cost $8,000 to build conventionally, assuming you could even find contractors available to build it. The federal government actively encourages this repurposing through programs that prioritize veterans for Quonset purchases. If you served, if you can prove you need housing, you can buy a surplus Quonset hut and have it delivered to your property. By late 1946, suburban developments made entirely of Quonset huts spring up around every major city. Roger Young Village in Los Angeles houses 750 families in converted military huts arranged in neat rows with streets named after battles and campaigns. Vetville developments appear near universities, where the GI Bill floods campuses with students who need immediate housing. The architectural adaptation gets impressively creative. Families add wooden facades to the curved ends, making structures look less like military surplus and more like quirky cottages. Interior walls divide the open space into bedrooms, living areas, and kitchens. Windows get cut into the steel sides, technically violating every structural principle, but making the spaces actually livable for family life. Some owners go further, burying the entire structure halfway into the ground for earth-sheltered insulation, or connecting multiple huts end-to-end to create sprawling compound homes. The flexibility of the basic design allows modifications that would be impossible with conventional construction. Housing inspectors and building code officials initially balk at approving these modifications. These structures weren't designed as residential housing. They lack proper foundations. They violate numerous building codes written for conventional wood frame construction. But the housing shortage is so desperate that municipalities reluctantly grant permits. The alternative is families living in cars or crowded into inadequate housing. A Quonset hut with modifications is better than no shelter at all. Churches discover Quonset huts solve a different problem, providing worship space for exploding suburban populations without the decade-long capital campaigns traditional church buildings require. First Presbyterian Church of Levittown, Pennsylvania holds services in a Quonset hut from 1952 until 1967, when they finally raise funds for a conventional sanctuary. Dozens of congregations make the same calculation. Spending $2,500 for immediate space beats raising $150,000 for eventual grandeur. The acoustics are terrible, the aesthetics underwhelming, but people can gather for worship next month instead of next decade. Some of these temporary church huts remain in service for 30 years, outlasting the generations who first considered them stopgap solutions. Education sees similar adoption. Post-war school enrollment explodes as the baby boom hits, and school districts face the same impossible math that plagued the military in 1942. They need classrooms immediately. Conventionally built schools take years to design and construct. Rural districts especially embrace Quonset classrooms. A single hut provides space for 30 students at 1/10 the cost of traditional construction. By 1950, an estimated 3,000 schools across the United States include at least one Quonset hut classroom. Some students spend their entire elementary education in these steel tunnels, learning multiplication tables and history lessons under curved ceilings that once sheltered B-29 King. TWI-9 crews preparing for bombing runs over Japan. Act 9. The Long Shadow. The commercial sector recognizes that Quonset huts deliver clear-span space without internal support columns, making them perfect for industrial work. Machine shops, auto repair garages, warehouses, and farm equipment storage all adopt the design. A welder can set up a complete shop in a surplus Quonset hut for less than 2 months' rent in conventional commercial space. The structure provides weather protection and enough room to work without the overhead costs of traditional buildings. Agricultural use proves especially popular. The original Strand Steel Corporation, having helped design military Quonsets, returns to manufacturing civilian versions specifically marketed to farmers. Thousands of Midwestern farms add Quonset storage buildings for grain, equipment, and livestock shelter. The maintenance requirements are minimal. Hose off the exterior once a year to remove accumulated dirt and salt. Check the bolts occasionally to ensure they remain tight. The structure lasts indefinitely with this minimal care. This civilian adoption creates an accidental architectural legacy. Quonset huts become embedded in American visual culture as symbols of practicality over pretense, function over form, and make-do ingenuity. They appear in movies and television shows as shorthand for post-war optimism mixed with austerity. Architectural historians initially dismiss them as temporary eyesores, utilitarian structures with no aesthetic merit. But by the 1990s, preservationists start recognizing surviving Quonset huts as important examples of adaptive reuse and vernacular architecture. Several achieve historic landmark status, protected as representing a unique moment when military technology successfully transitioned to civilian life, and when architectural necessity trumped architectural fashion. ATCT 10. Echoes Forward Modern. Disaster zones tell you everything about why Quonset hut DNA keeps reappearing in 21st century emergency response. When the 2010 Haiti earthquake destroys Port-au-Prince, relief organizations face the same equation American military planners confronted in 1942. Immediate shelter for hundreds of thousands of displaced people. No existing infrastructure. No time for conventional construction. Conditions that destroy inadequate. Temporary housing within months. The solution that borrows directly from Quonset principles. Even when designers don't realize, they're channeling 1940s military engineering. Arched steel frames, corrugated metal panels, prefabricated components that ship flat and assemble quickly. The basic formula hasn't changed because the underlying physics and logistics haven't changed. Arched structures deflect wind better than rectangular ones. Prefabrication allows factory quality control. Modular assembly enables rapid deployment. The United Nations High Commissioner for Refugees currently uses shelter systems called RHUs, refugee housing units, that are essentially Quonset huts with 80 years of material science improvements. Instead of corrugated steel, they use insulated composite panels. Instead of bolt-together assembly, they employ snap-fit connections, but the core concept remains identical. Curved profile for structural efficiency and wind resistance. Self-supporting arch, eliminating internal framing. Flat-pack shipping allowing massive quantities to reach remote locations. Assembly by unskilled labor with minimal tools. A two-person crew can erect a modern RHU in 4 hours, almost exactly matching the 1942 Quonset specifications. These units currently house over 200,000 displaced persons in refugee camps across Africa, the Middle East, and Asia. Hurricane-resistant construction has rediscovered arch geometry after decades of building conventional rectangular structures that hurricanes repeatedly destroy. After Hurricane Katrina devastated the Gulf Coast in 2005, engineers studying which buildings survived found that curved structures consistently outperformed rectangular ones. The Mississippi coast saw entire neighborhoods of conventional homes reduced to foundation slabs, while a handful of Quonset-style metal buildings stood intact with minor damage. This empirical evidence triggered research into what structural engineers call aerodynamic architecture, designing buildings that work with wind forces rather than resisting them through brute strength. The result looks remarkably like a Quonset hut because the physics haven't changed. Wind flowing over a curve creates less pressure than wind, slamming into a flat surface today exactly as it did in 1942. The WHO modern tiny house movement unknowingly reinvents Quonset principles when designers seek maximum interior space with minimum materials and cost. Several companies now manufacture arch-roofed prefab cabins using the same corrugated metal and self-supporting curve that Otto Brandenburger pioneered. These sell to buyers seeking affordable housing, disaster-resilient structures, or off-grid living solutions. The marketing emphasizes sustainability and modern design, rarely mentioning that the fundamental architecture is an 80-year-old military shelter. Some high-end architectural firms have even rehabilitated the aesthetic, designing luxury versions with floor-to-ceiling glass end walls and premium finishes that cost $300 per square foot while maintaining the signature curved profile. The arch has gone from utilitarian necessity to design statement. Military applications never actually stopped. The U.S. Armed Forces still deploy arch-style shelters in conflict zones. Afghanistan, Iraq, and classified locations feature modern descendants of the original Quonset. Current military specifications call for units that can be helicopter-lifted to mountain bases, assembled in combat conditions, and survive IED blast waves. The materials have evolved: aluminum alloy frames, Kevlar-reinforced panels, integrated climate control systems. But if you showed a 2025 military deployable shelter to the 1942 Quonset Point engineering team, they would immediately recognize their own design philosophy. The recent innovation is expandable versions that deploy from shipping containers, unfold like origami, and lock into rigid arch structures within an hour. The geometry remains fundamentally unchanged because it still represents the optimal solution to the same problems. Epilogue: Mars and beyond. Perhaps the ultimate validation comes from space exploration, where NASA and private space companies designing Mars habitats keep independently arriving at Quonset-like solutions. Proposed Martian shelters feature arched profiles to resist the planet's severe dust storms. Prefabricated components that ship on spacecraft where every pound matters. Self-supporting structures that don't require extensive foundation work in Martian regolith. The constraints of interplanetary construction mirror Pacific Theater challenges of 1942 with eerie precision. Extreme environments, minimal tools, unskilled assembly by people trained for other tasks. Maximum strength from minimum. Materials. Engineers working on Mars architecture independently rediscover the same solutions because physics and engineering fundamentals remain constant regardless of which planet you're building on. When humans finally establish permanent shelters on another world, there's a reasonable chance those structures will owe their design heritage to 30 engineers working in a Rhode Island warehouse during the darkest days of World War. Those engineers solving an impossible problem with corrugated steel and brilliant simplicity created something that transcended its immediate purpose. They designed a building system so fundamentally sound, so elegantly efficient, that it keeps working across contexts and decades, and even potentially planets. The Quonset hut succeeded not because it was pretty or comfortable or what anyone wanted. It succeeded because when you strip architecture down to pure function and optimize ruthlessly for performance under constraints, you discover principles that remain valid regardless of changing circumstances. 80 years later, every time a disaster strikes and relief organizations need immediate shelter, every time refugees need housing that won't blow away, every time engineers design structures for extreme environments, they rediscover what Otto Brandenburger and his team figured out in 60 frantic days in 1942. Sometimes the most lasting solutions emerge from the most desperate circumstances, and sometimes a curved steel tunnel built to house soldiers at war becomes a permanent part of how humanity shelters itself against an uncertain world. The Quonset hut wasn't just a building, it was a principle, and principles, when they're right, have a way of lasting long after the specific problems that created them fade into history.